Welcome to Empowered Learning. This is the second video in the study of the three-dimensional coordinate system, where we're looking at things with Cartesian or rectangular coordinates. So in this video, we are going to go over several examples. And so I have the first example showing here. As much as I can, I'm also going to do some visual demonstrations of what these answers are, just so that you can connect the words with what it would actually look like. And so this first example here says we want to give a geometric description of the set of points in space whose coordinates satisfy the given pair of equations. And so for this first example here, we see that we have the pair of equations x equals 1 and y equals 0. Okay. Now, please understand here that we are talking about 3D space. Okay. So in short, here we are talking about a plane, and here we are also talking about a plane. And so if we think about this, if we were in two-dimensional space, if we had two equations of a line, kind of like if I had, let's say, x plus 3y equals 6, and let's say x plus y is equal to 9, and I said, hey, let's figure out what points x and y coordinates would actually meet both of these conditions simultaneously, then of course you know that this is basically trying to find out where these two lines intersect. Okay, well, here what we are essentially saying is, where does these two planes intersect? Okay, and if I have a plane that looks like this, and then let's say I have another plane that kind of looks like this, then where those two planes are going to intersect at is going to be at a line. Okay, so these two planes are intersect at a line. Our job is to figure out what that line is going to be. Okay, or a way to describe that particular line. Now, I'm going to move over to the graphs of the fundamental planes that we had, so that we can actually see that and see how I end up getting the answer here, that this is going to be the set of all points is aligned with any point 1, 0, 7, such that z is a real number. And that is to say that it's going to be in the xz plane and parallel to the z-axis. Okay. All right, so let's move on over to that. Okay, so one way we could look at this question here is, let's say if x is 1 and y is 0, then we know that this particular point here could possibly be on that line. Okay, it's not the only point, but it is one of the many points. So I know here x has to be 1, y has to be 0. So I go 1 unit over in the x direction from the origin, and I go nowhere in the y direction. So since z can be any real number here, then that means that any point that's on this line going up or down would actually be the line that I want. Okay, and notice that that particular line is on, and I know it doesn't look that way here, downward, but this line is actually on the xz plane. Okay, it's actually on the xz plane, and of course in this case it ends up being a vertical line, and of course z could be anything. So that's why we could describe that set of points there as a line in the xz plane that would have these coordinates here. Okay, So that's one of the many ways we could describe that. So if we wanted to get specific here and actually just choose a point, one thing that we could say to just make it nice and succinct is to say that we want the set of all points So we want the set of all points that would be on this XZ plane and have this point in it, okay? So that's one way that we could answer that. All right, so let's move to the next example here. So this next example, notice that we have x squared plus z squared equals 4, and y is equal to 0. Now, if we look at this closely, notice that this looks very similar to x squared plus y squared equals 4. And if you remember, what this particular equation is just a circle where the center of the circle is the origin and the radius is 2. But what's different now is that we know that this is a circle that's in the XY plane. So that means for here, this should be a circle in the XZ plane, okay? So this should be a circle in the XZ plane with a radius of 2. Now, what confirms that we're actually in the XZ plane is that we also were given that y is equal to 0. And we know by definition, the XZ plane is the plane where the x and z coordinates can be anything, but y has to be 0. And the reason for that, the reason that y has to be 0 is because the XZ plane contains this point 0, 0, 0, okay? And so for the XZ plane, it's this one that holds everything together. So for this next example here, notice that what we're given here is this equation. And so this should look very similar to this equation here. And of course, what I'm writing is the equation of a sphere. Okay. So if we look at this, we know that since we just have x squared here, our x sub 0 is 0. And since we just have y squared here, our y sub 0 is also 0. And for our z sub 0, we would have to have z minus z sub 0. So this is like z minus a negative 3. Oops, that kind of got away from me there. So this would let me know that my z sub 0 would be a negative 3. Of course, here, the radius for this, which we're calling a, is going to be 5, the square root of that. And we see here that we have y is equal to negative 4, okay? Now, because y is constant, what that's going to do is bring this down a dimension, okay? So at first we're looking at a sphere, but if we hold that y coordinate there, we go from having something that is in 3 dimension to having something that is in 2 dimension, okay? And so we're still going to keep the x sub 0, y sub 0, and z sub 0 here. So I'm going to note that here. So that's still going to be 0, 0, minus 3. We'll keep that. But now what I can do is actually plug in that y is equal to negative 4 and figure out what I actually have in 2 dimension, or in the 2D space. And in the 2D space, of course, a sphere in 2D space is just going to be a circle. So we're just going to figure out what type of circle we have. So here, if I let y equal negative 4, have this situation here. That's a 2. That's 25. Of course, negative 4 squared is a positive 16. And if I subtract 16 from both sides here, then what I'm going to end up with on the right-hand side of this equation is just going to be a 9. On the left-hand side, I'll have this situation here. And thus, now what this looks like is a circle. But that circle is going to have a center of 0, negative 3. In other words, we take the x and the z coordinates here. And the radius of that circle now is going to be the square root of 9, which is 3. Okay. So since we know that x and z can be anything, this would actually be a circle in the xz plane. Okay. So this ends up being a circle that is in the xz plane that is centered about the point 0, negative 3, and its radius is also 3. So for our next example, this should look very familiar. We have y is equal to x squared. We know that that's just a basic parabola. Of course, if we were to kind of draw it out like how we would in pre-cal, this parabola would basically look like this. So it's a parabola in the xy plane. And by definition, we know it's in the xy plane because z has to be 0. So if you remember, in xy plane, z has to be 0 by definition. So this is essentially parabola y equals x squared in xy plane. Okay, nothing fancy about that. So for this next example here, we want to know what's the set of points that can be characterized by z is equal to y squared and x is equal to 1. Okay. Now, here we know that z equals y squared is also a parabola. Okay. But it is going to be a parabola in the yz plane. And how do we know that? Because we have the coordinates or variables y and z. Now, the thing is, we know that this particular parabola is in the yz plane, but we also have to hold x to be equal to 1. So if we want to get a visual of what's going on here, let's first figure out what z is equal to y squared is going to look like. So we know that this has to be in the yz plane. So if we were to draw a parabola where the z is acting like the y value and the y is acting like the x value here, then we would have something that looks like this. So we have a parabola going that way, and of course through here we have that, and then a parabola would go like that. Okay, that's what it would look like if it was actually on the yz plane. However, it's required that x is equal to 1. And what that means in 3D space, remember this is a plane. So what this is telling you is that we want a mirror image of this particular parabola on this particular plane. So the set of points that we're looking at is actually going to be a set of points that are going to be in a plane that is parallel to the yz plane. So that plane will look something like this. It'll be parallel to it, and it'll have this same parabola on it. Okay, so the points that are on the yz plane here, you can just imagine those points being lifted off of the yz plane and being shifted 1 unit up on the x-axis, and they basically slam into this particular plane here. So what it'll essentially look like here when we draw it is that this will be the plane x equals 1, and we'll have this parabola on it. Okay, and of course all the points that would be on this particular parabola would be of this form. The x coordinate would have to be 1. Your y coordinate would be whatever it would be, but of course your z coordinate would be the square of your y coordinate. Okay, so a way that we could describe the set of points, it would be the set of points that is on the plane x equals 1 that have points that look like this. Okay, that's one way to describe it. Another way to describe it would be all the points on the parabola z is equal to y squared. That is on a plane parallel to the yz plane by shifting it by 1 unit. Okay, so you got several different ways you can say it. The main thing is just to know that whatever the plane is going to have a set of points on there that looks like a parabola, and they're going to follow this particular profile as far as the points are concerned. Okay, so for our second set of examples here, we want to describe the set of points in space whose coordinates satisfy the given inequalities or combinations of equations and inequalities. So for these first two examples here, I've actually done a visual. I've drawn it right next to what we're talking about here so that we can kind of get an idea of what we're talking about. So first thing that we see is that we have this inequality here, and know that y is equal to x squared. That is just a parabola. Okay, so that would be this graph right here when y is equal to x squared. Now, the greater than part comes into play because if we want all the points that are above the parabola, that would be all of these points down here laying on the ground, so to speak. Okay, so if we were just looking at the case when y is equal to or greater than or equal to x squared and z is equal to 0, what we would have is something that would look like this. Okay. However, we're told that z could be greater than or equal to 0. So not only are we considering these points here, we're considering all the ones that are above it vertically. Okay. And so that's why I had drawn this little 3D solid figure here to show that we have more than just the points that are kind of lying on the XY plane. We have all the points that are above it as well. Okay. And so a way that we could describe that is to say it's a set of points that form a region of points that are on or inside y equals x squared in the xy plane, as well as all the points that are above. Okay. For example B, notice that this is also, I'm going to switch colors here, that this is also a quadratic inequality, and x is equal to y squared would actually end up being a parabola as well. Okay, that parabola, we know it is a parabola, but not necessarily a function. In general, in the xy plane, it would look like this. Okay, since we're told that we want all points that are either on the parabola, which is this, or this less than part, which meaning the x coordinates will always be smaller than the y coordinates squared. That's essentially everything, all the points here to the left of this particular parabola. Okay, so everything that's on it and everything to the left of it. Okay, and so if we were just looking on the xy plane, that is all that we would consider. But notice here that we also have that z can be anywhere from 0 to 2. So that means here, again, we have all these points that are not just on the xy plane, but we have points that are above it up until we get to z equals 2. Okay? And that's what this particular region of points would look like. All right, so for this next example, I won't do a visual, but we can pretty much figure out relatively easy what this is going to be. Notice that what this looks like is basically the left-hand side of the equation of the sphere. And we're actually dealing with two different spheres here. So we have x squared plus y squared plus z squared is equal to 1. And this is x squared plus y squared plus z squared is equal to 4. Okay. Of course, this one is a sphere with radius 1. This is a sphere with radius 2. And both of these spheres have a center that is at the origin. Okay. Now we know from pre-cal that whenever we have a compound inequality that looks like this, we call it a conjunction. A greater than or equal to B. Less than or equal to A, which is less than or equal to B, which is less than or equal to C. Then that means that A is less than or equal to B and B is less than or equal to C. Okay, so we have two overlapping intersecting sets, and so we want to know what values of B are in common in both. In this case, what we're looking at is we want to know what are going to be the points on the sphere, or in this case on the interior of the sphere that are going to be in common. So what we have here is a case where we're looking at x squared plus y squared plus z squared is greater than or equal to 1, and x squared plus y squared plus z squared is less than or equal to 4. This is the sphere that we talked about earlier, and I'll call this sphere A, call this sphere B. So this is going to be sphere B and its interior points. Okay. This is sphere A and its exterior points. Meaning, if we're looking at a sphere, I'll just try to draw one here. So if I had a sphere that looked like this, if I had a sphere A and its exterior points, then that means that I'm looking at the points that are outside of the sphere. So like all these points that are out here. Okay. For this case, we're looking at a sphere and all the points that are on the inside of the sphere. Okay. So what we essentially have here is a region of points that are going to be in common with both the interior of this particular sphere and the exterior of this particular sphere. Okay. So to make things simple here, the answer is going to be just the region of points enclosed between sphere A and sphere B. And I'm just calling it sphere A and sphere B just to shorten what I have to write. So for this next example here, notice that very similar to what we had earlier here, this is going to be a sphere with the center at the origin and radius equal to 1. So that's what it is if this was an equal sign. But of course, the less than sign here is going to say this sphere and its interior points. Okay. So that is what we're working with. So we have an entire sphere and all of its interior points. Now, if we take a sphere plus interior points, what that actually ends up equaling is a ball. Okay. And of course, most of you know what a ball looks like. It's just a solid figure. It's basically a sphere where the inside is filled in. Okay. And that's basically what this is saying here. Now, when we look at z is greater than or equal to 0, what that's telling us is that our z coordinate for our sphere has to be non-negative. Okay. So if I have a sphere, let's say I have a sphere here, and I know that this is going to be, let's say z equals, I'm just trying to make it easy to picture here. Normally we have z going up, but I'm going to make it look like this now. So if we had this like this where z is equal to 0, then of course z would be negative down here, z would be positive up here. So what we want is the case where we want the upper half of the sphere, okay? Or put another way, we want the upper hemisphere, okay? Because a hemisphere is just half of a sphere. And so we want the upper half of the sphere, or the half of the sphere where our z coordinates are either 0 or positive. Okay. So to do that, we could express everything in terms of z. So that means here I could actually solve this particular, I could solve this particular equation here for z. If I did that, then I would see that z squared is equal to 1 minus x squared minus y squared. And if I took the principal root of both sides, I would have z is plus or minus the square root of 1 minus x squared minus y squared. And since I want the upper hemisphere, or I want the hemisphere where all the x coordinates are non-negative, this would have to equal to the positive option here. Okay. So one way that you could describe, well, hey, what are going to be this set of points? It can be the set of points that satisfies this particular equation here. Okay. That's one way you can write it. Another way you could write it is you could say it's the set of points that all have this profile. So x could be anything, y could be anything, but z is going to be 1 minus x squared minus y squared. Okay. And so any point that would have, any point that fits this profile would actually be in this particular half of a ball. Okay. All right, so for our example number 3, the set of examples that goes along with that, we still want to describe the given set with a single equation or with a pair of equations. And so now this is going to go into what I was talking about when I originally introduced the fundamental planes and how we needed to be able to properly describe a plane in a succinct way so that we'll know exactly what plane we're talking about. So these problems kind of get into that. So we want the set of points in a plane that is going to be perpendicular to, and of course, the first example here is going to be perpendicular to the x-axis at this particular point, okay? Well, the first thing that we know is that because we want a plane that is going to be perpendicular to the x-axis, if we look at it, that particular plane, and I'll show you a visual here just to make sure that you follow what I'm saying. So if we're looking here, we know that if this is the x-axis right here, we know that the plane, the YZ plane, is the one that is perpendicular to the x-axis, okay? And of course, for the YZ plane, we know by definition, x would have to be 0, okay? Now, we were told that we had to have a plane that is perpendicular to the x-axis, but have this particular point in it, okay? So since it has to have this point in it, we know that x can no longer be 0. In other words, it can't be on the YZ plane. It's going to have to be on the plane described as x equals 3, okay? So it's going to have to be on a plane that kind of looks like this, okay? And so that point 3, 0 would be this point right here that I'm drawing, and I'll draw it in a different color so that it's able to be seen. So this would be the point 3, 0, 0. That would be that point. And of course, what you see here in the blue dotted line is my representation of the x equals 3 point, okay? So this is why I have a lot of writing here, but basically it's what I'm trying to describe. Since I want a plane that is going to be perpendicular to the x-axis here, I know the YZ plane and all planes that are parallel to that are going to be perpendicular to the x-axis. And so I just have to find the one that's going to have the correct point on it. And I just look at the x coordinate for that. So using that similar thinking here, if I want a plane that's perpendicular to the x-axis, then I know that x equals a number is going to be able to describe that plane. If I want the same thing, but now it's perpendicular to the y-axis, then the plane that's going to best describe that is y equals 1. And again, I'll show you a visual just to be able to show you why that actually is. All right, so for that second example here, we wanted a plane that was going to be perpendicular to the y-axis, okay? Well, we know in general, if this is the y-axis here, then the xz plane is perpendicular to it. It crosses the y-axis at a 90-degree angle. Of course, for the xz plane, y has to be 0, okay? But we want a point that has y is equal to -1. So, of course, what that means for us here is that we would have to have another plane that kind of looks like this. And of course, here it would have to have the point 0, -1, 0 on it. So it would actually be, this point would actually be right there. And so this black plane that I've drawn here would actually be the 1, okay, that we're referring to. But this would have to be described as y is equal to -1. All right, and so for our last example for this particular type before we move on, if we wanted a plane that is going to be perpendicular to the z-axis and have this particular point in it, using the logic that we've done before, we know that that would just equal to z equals -2. And of course, a simple way to think about this is that whenever we are talking, whenever we are describing a plane, we describe it as the coordinate that has to be constant. Okay, so for any plane that is going to be perpendicular to the z-axis, it has to have a constant z coordinate. Any plane that is going to be perpendicular to the y-axis is going to have a constant y coordinate. Any plane that is going to be perpendicular to the x-axis has to have a constant x coordinate. It's really just that simple. Okay, so for our next round of examples here, within example 3, we see that we want the plane or the set of points in a plane through where that plane actually goes through this particular point, but it's going to be parallel to, notice that the wording is changed, not perpendicular, but now it's parallel to the xy plane, okay? Now here I have that, we recall that planes that are parallel to the xy plane must have a constant z coordinate value, okay? Now I'm going to show you a visual to remind you of why that is. So we know that this is the xy plane. And by definition, the xy plane has to have z to be equal to 0 because this plane contains the point 0, 0, 0. Okay. Now we know that any plane that is parallel to the xy plane is also going to be a horizontal like plane as well. In other words, this plane here will actually either be on top of the xy plane or below it if it was, let's say, down here. Okay, so either way it's going to be parallel to it. Now because of that, since we had to describe the xy plane as the plane x equals 0, these other planes, whether it is going to be above or below, are also going to have to be described as x equals a number. Okay. Now, in this case, we just need to make sure that it has the z coordinate that this particular point has. And so for this particular plane that we're referring to that's going to be parallel to this one and contain this point, it must have z to equal 1. So we know that the resulting answer for this must be the plane z is equal to 1. Okay. And so that's why that ends up being that way. Now, if we look at this thinking and we kind of carry it on to the other examples, we're going to see that we can follow a pretty easy pattern here. Okay. If we have a plane that's going to be parallel to the xy plane, then of course it's going to have to be described with a constant z coordinate. So z equals whatever the z coordinate is going to be, that answer for that. Okay. If we did the same thing before the yz plane, the yz plane must be characterized as x equals a number. And of course, the x coordinate that we have is 3. So the plane that we'll be referring to here is going to be x is equal to 3. Okay. And lastly, if we're talking about the xz plane, the xz plane must be described in terms of the constant y value that it has. And of course, the point that we had has a y value of -1. So that means that the plane points that we're referring to is just going to be the plane y is equal to -1. So the last round of examples in example 3 asks for the set of points on a circle. And I just put the set of points on A in parentheses because most of the times when you see these problems in the textbook, they'll just say the circle. okay? But they're implying that there's going to be a set of points on that. So a set of points on a circle of radius 2, centered at the point 0, 2, 0, and this particular circle is going to be lying in and of course they'll give us the plane that we're referring to, okay? So basically we have a circle of radius 2 centered here, and we got to choose which plane is going to be on, what equation is going to describe it, okay? Now, if we are in the XY plane, then remember that in 2D, if we were talking about the unit circle, it would look like this, okay? If we were talking in general, that equation would look like this. And so we know that in the XY plane, Z would have to be equal to 0, okay? And of course, we see that we have Z is equal to 0 right there. So for this example, we're only considering the X and Y coordinate of where this particular circle is centered at, because of course we move from 3D to 2D, okay? So if we do that, we just let our H here be 0, let our K here be 2, and of course our R is going to be 2 as well, and we just end up with this particular equation here, which is essentially just the circle that has a center of 0, negative 2, 0, positive 2, and a radius of 2, okay? All right, so if we do the same thing, but for the YZ plane, now what's different is that X in the YZ plane would have to be 0. And of course, here you see that that still is happening. So the point that we are considering still has X to be 0 here, okay? Now, the equation now would have to look like y minus y sub 0 squared plus z minus z sub 0 squared is equal to a squared. And of course, for here, our y sub 0 would just be whatever this y coordinate is. Our z sub 0 would be whatever that z coordinate is. So this would be y minus 2 squared plus z minus 0, which would just be z squared. And then of course our radius 2 would be 2 squared, and that would just end up being 4. So we would just have y minus 2 squared plus z squared is equal to 4. That would be the equation that would describe the set of points on this circle of radius 2, but it would be on the YZ axis, YZ plane. All right, lastly, if we are in the XZ plane, then we know that Y would have to be 0 in this case. Now, if we pay attention to the point that we said everything was centered by, and let me make sure I copied that down correctly. Yep. So that's the point 0, 2, 0. Okay. So notice that if we're on the XZ plane, your Y won't be able to be 2. It would have to be 0 if we're on the XZ plane. Okay. Also note that since we're on the XZ plane, our equation of a circle formula would have to look like this. Okay. And so of course, this would be our X sub 0 value. This would be our Z sub 0 value. So this would just end up being X squared plus Z squared. And of course, our radius before, radius had a length of 2. So 2 squared is 4. And so this would be that final answer. Okay. We would not want to write, we don't want to write this as well, because the question is asking us what is the circle that is on the XZ plane? And of course, we can't have a Y coordinate of 2 on the XZ plane. Okay, it's just not possible. So you could state it, but it's immaterial because, you know, there is no point that's going to have a Y coordinate of 2 on the XZ plane. So for our next round of examples, with example number 4, we want to write inequalities to describe the following sets. And we're told that this first set is a slab bounded by the planes z is equal to 0 and z is equal to 1. Okay. Now, if you remember, if we're describing a plane in terms of a z coordinate, then that means whatever plane we're talking about is going to be parallel to the xy plane. Okay. Now, to kind of remember what that looks like here. So this is our YZ plane. So that means any plane that we're talking about is either going to be below it, like this, horizontal, or is going to be above it, like this, and still lay horizontal. Okay. So we know that. Now, in the problem that we were given here, and I'm going to erase these planes here because I'm going to have to draw some more a little bit later. So in the problem that we were given here, we were told that we want a slab, or this is just basically a region of points that's going to be in between the plane z equals 0 and in between z equals 1. Okay. Now, of course, the z equals 0 plane is the xy plane. If we were to go up 1 unit and then sketch out what that plane looks like, plane here, this would be the z equals 1 plane. Okay. And so what it is that we want is we essentially want all these planes that are in between here. Okay. So all these planes that are in here, that is what we're interested in. And so all those planes, we want the ones that are strictly in between the xy plane and the xy plane, or better known as the z equals 0 plane and the z equals 1 plane. Then we could just simply say that we want the planes that are in between the planes where the z values are in between 0 and 1. Okay, you could express it this way, or you kind of express it this way if you want to do it in interval notation. Okay. All right, so that's why here I have this answer expressed both this way or this way. Both are correct. Now, if we're using similar thinking here, I want the slab bounded by the planes y is equal to -5 and y is equal to 3. And notice this time the planes are included. In the last example, the planes were excluded. So that's why I just have the less than signs here instead of the less than or equal to. But for this one, notice that planes are included. So I have to actually include the plane y is equal to -5 and y is equal to +3. So that means that I would just essentially have all the planes from y equals -5 all the way to y equals 3 and those included. And this is the most succinct way to be able to explain that in 3D coordinate notation. All right, so for the next example, we are looking for the half space consisting of the points on or below the XY plane. Okay. So here we know that when we talk about the entire space, we're talking about the 3D space, is going to look a lot like the picture that I had shown you in the first video where we were looking at the octants. And so I'm going to go back to the plane, well, the graphs with the fundamental planes on it again, because that'll be able to better describe what I'm talking about here. Okay, so one way to think of this is remember that these are just 3 planes in our entire 3D space. And of course, anything that is on or below the x-axis here would be in what's called, I guess, the bottom half space. Okay. Now, if we go and look at what the octants look like, we'll see the half space looked at in a different but similar way. So if we look at these octants here, the half space, we have 2 half spaces here. And so all of it is going to be divided by the XY plane. Of course, the lower half space is the 4 different octants that are below the XY plane. And of course, the upper half space would be the 4 octants that are going to be above the XY plane. So that's what that particular problem is referring to there. So now when we say we're considering the half space, we just need to know, are we talking about the upper half space or the lower one? Okay. And so we want the one that is going to be on or below the XY plane. So now we know that we're talking about the lower half space as well as the XY plane itself. And of course, the one thing that we know about the lower half space here, and I'll go back to that, is that if we were to continue to stack planes that are on the lower half space, all these planes here that I'll be stacking, all of them would have z coordinates that are less than 0. Okay. The only one that wouldn't be that would be the XY plane. And the XY plane, by definition, has z is equal to 0. So what that means for us here is that for our problem, all the planes that meet the condition of z being less than or equal to 0 are going to be a succinct way to be able to describe the lower half space. Okay. All right. So for example D here, we want to consider the upper hemisphere or the upper half of a sphere of radius 1 and have it be centered at the origin. Okay. Well, for starters, we already know that if we wanted to have a sphere that had a radius of 1 and centered at the origin, it would look like this. Okay, we already know that. Now, if we wanted the upper hemisphere or the upper half of the sphere, then of course we'll just be looking at the top half of that. Okay. Now, I'm going to try to draw a sphere here again. Okay. So what we want is this upper half. Let me try to switch colors here. So I want all this business here. Everything that's up at the top. Okay. And of course, if I want everything that's up at the top, one of the things that I know is that if I want everything that's up at the top, I know that my z values here are going to either have to be greater than or equal to 0 in order to talk about those points that will be in the upper hemisphere. So now that makes this relatively easy to do, but this should also look kind of familiar to you because we've actually dealt with a problem that the wording was different, but the outcome is very similar. And so I'm going to go back to that. We had an example, and that example was a 2D. If you're following along and actually writing it down, I'm going to skip to that now and show you how what we did then is very similar to what we're doing now. So if you remember this example here, and I'm going to erase a bit. Remember that we were asked to come up with, we were really supposed to come up with an equation or a combination of equations and inequalities to try to describe the set of points here. Remember, this was just our sphere, x squared plus y squared plus z squared is equal to 1, and all of its interior points, okay? But here, we restricted those interior points to being the ones that have non-negative z values, okay? Which, of course, is essentially the upper half of a sphere, okay? So, and that is exactly, I'm going to try to go ahead and switch back to, wait a second here, lost my pen. We go switch back to here, let me go back down. That's exactly what this is, okay? So my point here is that the same way I dealt with this problem before, I'm going to go back to it again here. The same way that I dealt with this problem by going here and solving for z is the exact same way I would deal with the problem that we're doing now. Now for this problem, the example 2D here, I could have just wrote this as this is going to be the sphere x squared plus y squared plus z squared is equal to 1 and all its interior points. Now that is like the nice succinct way to write that, but we could have wrote this way as an equation as well, because technically it is an equation. If we wanted to make this an inequality, I could just say z has to be greater than or equal to this, but that would actually be incorrect because here we want z to be exactly equal to this. So that's why I left it as an equation and I didn't try to express it as an inequality, okay? So I'm saying all that to get to the point that the answer to this is just going to be z is equal to square root of 1 minus x squared minus y squared, okay? All right, so next what we need to do is find the distance between 2 points in 3D space. And of course, we know that, let's say the distance in between some point P1 and P2 is just simply the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay, so we can just label this x1, y1, z1. I don't know why I can't draw z's today. And this will be x2, y2, z2, and we'll literally just plug it in. Okay, so the distance here, so our x2 is 2, x1 is minus 1, so 2 minus a negative 1 squared plus y2 minus y1, so 5 minus 1 squared, and then z2 minus z1, so it's going to be 0 minus 5 squared. Make sure I did that right. Yep, okay. Then, of course, this subtracted negative is the same as addition. 2 plus 1 is 3, and 3 squared is 9. 5 minus 1 is 4, and 4 squared is 16. And 0 minus 5 is a negative 5. Negative 5 squared is a 25. And of course, if we add that up, we'll get square root of 50, which is the same as square root of 25 times square root of 2, which ends up just being 5 times the square root of 2. So that's pretty simple. Now, my next example is just another example of doing the same thing. As you can see, I label my x and y and z coordinates, plug it into the formula again, and we see that this time we end up getting 7 as an answer. Okay. I know this is relatively easy, so I'm not going to spend a whole lot of time on that. We'll go ahead and move on to something else. So next, what we want to do is kind of do something like what we did in pre-cal when we were given the standard form of an equation of a circle, and we wanted to extract out what the center and the radius would be for that particular circle. Well, we want to do the same thing, but do it with a sphere. Okay. So again, we know that the formula in general is just going to be x minus x sub 0 squared, y minus y sub 0 squared, plus z minus z sub 0 squared is equal to a squared for the standard equation of a sphere. So from that, we know that our x sub 0 is going to be square root of 2. Our y sub 0, since this has to be y minus a negative square root of 3 here, that would be a minus square root of 3. Z sub 0 is going to be a negative 2 for the same reasons why this was y minus square root of negative 3. And we know that 3 is a squared. So that's going to tell me that a is just square root of 3. And I'm choosing the positive version of that versus the negative because we know radius is length. And length can never be negative. So from that, we know that the center of our circle now, center of our sphere now is going to be square root of 2, negative square root of 3, negative 2, and our radius, that is just going to be square root of 3. Okay. All right, so for our second example, very similar. For this first term, since we just have x squared, we know that our x sub 0 is 0. We know that this has to be y minus a negative 1/3. So that means our y sub 0 would be minus 1/3. And here, this fits the form z minus z sub 0. So our z sub 0 would be a positive 1/3. Of course, here, this is going to be our radius squared. So if we took the principal root of 16 over 9, we would just take the square root of 16, which is 4, square root of 9, which is 3. And of course, we choose the positive one because the positive answer because we wanted to represent length. So our center is just the point 0, negative 1/3, 1/3, and our radius is just going to be 4 over 3. All right, so for example 7, we're going to go in the opposite direction. We're given the center, and what we want to do is figure out what given the center and the radius, and what we want to do is figure out what the equation of the sphere is. Okay, so we know here that this would be our x sub 0, y sub 0, z sub 0, and our radius, this would be a. So therefore, a squared would be 4 squared, which is 16, and square root of 3 squared, which would just be 3. So our equation would just end up being x minus 1 squared, because the x minus x sub 0, plus y minus y sub 0, and a minus a negative 2/3 is a positive 2/3. We square that. And then z minus z sub 0, which is 5. We square that. And then, of course, our a squared here would be 16/3. And so this would be what our equation of the sphere would be for this situation. So for example 8, what we want to do is find the centers and radii of the spheres given below. And I mentioned here that what we're given is the general form of the equation of these spheres, okay? And I know I talked about this, I believe I talked about it in the first video here, but I may have mentioned it here in the second one. But we know that the general form of the conic section equation in 2D looks like this, okay? In 3D, that equation looks like this. And my whole point of mentioning that is that whenever we get the standard form of a circle, an ellipse, hyperbola, a parabola, all that stuff in 2D, what we are essentially doing here is working on this general equation here and doing a bunch of completing the square and making some assumptions about the coefficients a through f to be able to know, all right, are we dealing with a a circle or an ellipse or hyperbola or whatever, okay? So for instance, whenever we're dealing with a circle, we know that whatever a and c are going to have to end up being would be equal. Ideally, they would be equal to 1, but of course, they would need to be equal in order to make that work. So that's some of the things that we know. So in this example here, we're doing the same kind of thing that we would if we were trying to find the equation of a circle and we had the equation of a circle in this form and we needed to transform it into the standard form, okay? So I've worked out this first example here, and if you see the main thing that we're trying to do is all terms with x, we get those together. All terms with y, all terms with z, get those together, and then all the numbers we put on one side. And so here what we need to do is force these two terms here to be a perfect square. So we introduce a third term, and that's just going to be 1 times whatever this is. And of course, the completing the square method basically says whatever this number is, you divide it by 2 and then square it. And that's what you put here. So we put that number there and also here. And of course, this number here is 1 times all that. So now we've actually forced a perfect square for those first 2 terms. We know that that comes out to be x squared plus 4x plus 4. And if we factor x squared plus 4x plus 4, it's just x plus 2 quantity squared. And of course, on the right-hand side of this equation, we get 4 plus 4 is 8. And then it's just a matter of interpreting it from there. This is an equation of a sphere where the center of our sphere is going to be at the point -2, 0, 0. And of course, if we take the square root of 8, that is going to be the corresponding radius. And of course, square root of 8 is, in simplified form, is 2 times square root of 2. Okay. All right, so we're going to do one more example of that here. And so for this one, we're going to take the same strategy here. So notice that we have these terms with y and z in it here. So I'm going to say 3x squared plus, and then I have 3y squared plus 2y. And then I'll have 3z squared minus 2z. And that equals 9. So before we get into trying to do the completing the square thing, we have to get it into the correct form, which means we're going to have to factor out a common factor of 3 out of both of these two groups of terms. So the first term stays the same. We factor out a 3 out of these first two terms. And we factor out a 3 out of the second two terms. Okay. Now, from here, we can see that we have a common factor of 3 in all terms on the left side. So I could just simply divide both sides by 3 to make this real simple. And that will just be x squared plus y squared plus 2/3 y. And I'm going to go ahead and add this blank here now. That will be z squared minus 2/3 z plus another blank. And this is 3. Okay. Now, I'm not finished yet. What I've done here is I've set this up so that I can do the completing the square. And so part of the reason why I went ahead and I divided both sides by 3 is so that I can make this whole process of doing completing the square a little bit easier to handle. If I would have left the 3's in, then I would have had to account for this number that's going to be in the blank here. I would have had to say 3 times that over here on this side. Okay, but since I've already taken care of the 3's, then this is going to be the number that goes in the first blank. That's the number that's in the second blank. To balance this out in doing the completing the square, I need to introduce the same thing over here. And of course, these numbers 1 and 2 that are circled is just to keep track of what number it is. Now, once we're here, of course, we do the whole completing the square thing. We take whatever number this is, we divide it by 2, and we square it. So if I take 2/3 divided by 2 and then square it, and of course that's the same as 2/6 squared, which is the same as 1/3 squared, which is the same as 1/9. Okay, and the only difference in between this number here and the other one is that this would be a minus. So that would be a minus here, that would be a minus there, but I would still have a positive 1/9 there. So that means here I would have 1/9 here and 1/9 here. Okay. So once that's done, then of course everything else is relatively easy because we already know what the outcomes are going to be. If I write down x squared, and I know that whenever I have a perfect square here, it is always y plus whatever this number inside the parenthesis is. And of course, for this first one, if you remember, it was positive. So this would be 1/3 quantity squared. For this second group here, this would be z plus a negative 1/3, because of course this number here was negative, and of course plus a negative is the same as subtraction. So I'm just going to rewrite this as z minus 1/3, and then quantity squared. And then of course here we know that this just ends up being 3 plus 2/9. Okay, and 3 plus 2/9, if we look at it, that's just going to be 29/9. And so the last thing that we would have to do here, of course, is if I want to figure out what the radius is going to be, it's just going to be the square root of whatever this number is. So to get to the answers that we want, the center of this particular sphere, The x coordinate is going to be 0 because we just have x squared here. The y coordinate is going to be a minus 1/3 because we have y plus 1/3, which is the same as y minus a negative 1/3. The z coordinate is going to be a positive 1/3 because we have z minus 0. And then our radius here is just going to be the square root of what we see here. So the square root of 29 is just square root of 29. Square root of 3 is just, square root of 9 is going to be 3. And so this would be our final answer for that. All right, so we are getting close to the finish line here. So next to last set of examples ask us to find the formula for the distance from a point, the general point XYZ to a point that's given on the axis that's told to us. So one of the things that we know is that if I have some general point X, Y, Z, and I've been told to say, well, been asked, hey, find the distance in between this general point and a point that's on the x-axis. Well, I know all points on the x-axis are going to have 0 for the y and z coordinate, okay? So it's essentially looking at these 2 points and doing the distance formula in 3D space for it, okay? And of course, if I label this x1, y1, z1, x2, y2, z2, and plug everything in, and actually I think when I worked this out, I actually did it the other way, but it still ends up being the same thing. We end up getting square root of y squared plus z squared. And that makes sense because the difference in the x coordinates is 0. So of course, that would be immaterial to the calculating of the distance in between those 2 points, okay? So notice here, if I have a general point and I'm looking the distance in between a general point and a point on the x-axis, notice that my formula here does not include x as a variable in it, okay? So if I was to take that sort of thinking here and say, now I want the same thing, same situation, but now I want a point that's going to be on the y-axis, is going to look like this. And of course, the y variable is the one that's not going to be there. So the distance in between those 2 points now would just be square root of x squared plus z squared, okay? And then, of course, if we did the same thing, but now we want to measure a random point, the distance in between that and a point on the z-axis, then, of course, it is the z variable that isn't included. And we see that the distance in between those 2 points is just square root of x squared plus y squared. All right, so if you've been watching this since the beginning, thank you so much for sticking in there. We now are at a final example, and here we want to find the point on the sphere that's given to us, and it's going to be nearest to the xy plane, okay? Now, notice that, first of all, this is a sphere that has a center of 0, 3, -5, and a radius of 2, since square root of 4 is 2. If we compare that to the points that are on the xy plane, remember that by definition, points on the xy plane have a z-coordinate value of 0. Every point on the xy plane has a z equals 0 z-coordinate on there, okay? So if we think about that, this is a sphere, and I'm going to just call this A here. So I got this sphere here. And I know that in any direction, I know that the points that are actually on this particular sphere, and let me make sure that that is known. I'm going to switch colors here. So the actual points that will be on the sphere are going to be all of these, along with everything that's on the surface here, okay? So basically the surface area of this ball looking shape, okay? Now, we know that if we just look, up, down, right, and left, that I have a point that's up here, point that's down here, point that's right here, point that's right here, okay? Now, I got, points in all directions, but I'm just saying in terms of X, Y, and Z axis, I could look at these particular points here. If A is going to be the point 0, 3, -5, and my radius is 2, this point at the top of the sphere is going to be 0, 3, -3, okay? This point over here to the right is going to be 2 units, let's say, I guess if we're looking at this in terms of the I want to say Y direction, because we're kind of looking at our convention like this. We're just doing in terms of the Y. This would be 0, 5, -5, and this would be in the negative Y direction. So this point here would be 0, 1, -5. And of course, if I was to come out of the page at this particular point here, that would be the movement on the positive x-axis. So this would be 2, 3, -5, so on and so forth. Now, my point in saying all this is that I want to pick a point that is going to be on this sphere, but is going to be closest to the XY plane, okay? Now, the XY plane, remember, has coordinate of z is equal to 0. So it should be clearly above this particular sphere, okay? So because of that, the XY plane is lying up here. At z equals 0. Now, because of that, we know that this particular point, the point 0, 3, -3, is going to be the one that's closest to it, because there is a direct vertical line up to that particular plane. The rest of the points, even though they do have a point that can match up to them going vertically, is going to take more length or more distance to get there to the XY plane than that point 0, 3, -3. So for that reason, we know that the point that is closest to this particular sphere, closest point, is just going to be 0, 3, -3. Okay. All right, so for the final example here, we want the same situation here. We have this same sphere, but now we want the point that's closest to 0, 7, -5, okay? So again, we have a sphere. And the center of that sphere is going to be 0, 3, -5. The radius of the sphere is 2. Okay. Now, if you look closely here, one of the things that you should recognize is that both of these spheres, sorry, not both the spheres, but both of these points, the point that we have to get closest to and the center of the sphere, they both have the same z coordinate, okay? So if I'm looking at this sphere here, I know that both points that I'm considering here, the center and this particular point that I need to get closest to, is going to be on the same plane. Okay. And matter of fact, it's going to be on the plane z equals -5. I know that. Okay. So ignoring z equals -5 here, I have a point here. Well, let's do this first. So I have the point, the center of the circle here. I'll just call that A. I know that for my sphere, the point that is going to be on the sphere, that is a distance of 2 away from this particular point here, which is going to be point B. Point B is going to be 0, 3, and then I take 2 away from this particular 5 here. So if I take 2 from that, I would have 0, 3, -7 going in one direction. If I go in a positive direction, I'll be adding 2. It'll be 0, 3, no, I messed it up. Hold up. So I know that the z coordinate is going to be the same, but we have to add 2 to the y coordinate here. So I have to add and subtract that. So this one would be, if I said 3 minus 2 here, that's going to be a 1. And that would be -5. And for point C, this is going to be 0 again. And we would add to this, that would be 5, -5. Okay. Now the point, and we'll just call this D, the point 0, 7, -5 is actually going to be over here. Okay. And so of course point C, which is 0, 5, -5, would be the point that's going to be closest to that. And so that's why that should be the final answer for that. Okay. And so our answer here would just be closest point is going to be 0, 5, -5. Okay. And again, we figure that out because we know that the center of the sphere and the point that we need to get closest to are all on the same plane. And so then we could just kind of construct what I've done here and just see which one would be closest. All right, so this concludes our study of the three-dimensional coordinate system. Remember that we've talked about not only the how an actual point is defined in this coordinate system. In the first video, we went over distance formula for distance between 2 points, sphere, standard equation for a sphere. And of course, in this video, we did a lot of examples to try to show how we could actually use that knowledge practically. Take care.